Ladies and gentlemen, welcome to lecture 15.2 in the Math 4000 problem solving for Putnam. As you have seen last time when we talked more about the integration, we've dealt with the first and the second mean value theorems for integrals. And now in this lecture, probably this will be a little bit of a longer lecture. I'd like to draw your attention with some facts about the integral inequalities. This will be a very important topic in this course. And throughout the lecture, I will show you a bunch of techniques on how to deal with certain integral inequalities. Well, I will start with the most basic ones. And we will see plenty of applications with on different Putnam problems or some other problems as well. And like I said, let me start with something basic first, and then we'll see some other fancy integral inequalities. And the first inequality that I have in mind is the following. So let me start sharing the the screen. So as you can see, I will talk about integral inequalities. And first thing that I would like to start with, which is the most basic, if you want to put it this way, integral inequality is the following. So the most basic, let's call this zero. The most basic inequality for integrals is the following. So let's suppose I have a function, so f defined on a interval a, b, right? And let's say this function is integrable such that is non-negative for all x in AB. Then obviously we have this inequality that the integral of f on the interval AB is non-negative. That's obvious. So there is no way for the function, for the integral to be negative or something like this. So if the function is non-negative, then its integral is non-negative. And of course, let me point out a remark here. And this will be a very important remark because from this remark we can derive certain inequalities. If I have a function, and let's just say a continuous function this time, then the integral from a to b of the square of f is non-negative, right? So the integral is non-negative. Well, and let's just say here with equality, if and only if the function is 0. For all x in AB. Anyway, I will not insist with the proof of the equality case. I think you will learn this in any introduction to analysis course or in any advanced calculus course. I think I taught this at Texas Tech last spring. I think it was Math 4351 Advanced Calculus 2. And when I talked about integration, I also proved this fact. So those of you who are interested in this, you can actually go and look at the syllabus, and you'll find it there. You'll find in the book. I think the book we used was Barnes and Sherper. I think, I don't know, it's Introduction to Analysis or something like this. But anyway, you'll find this fact and the proof of this fact in any introduction to analysis course. All right, so that's the most basic inequality. And from this basic inequality, especially from the remark, we can derive the first one. So one, it's what we call Cauchy-Schwarz inequality. All right, so we have seen Cauchy-Schwarz inequality, I think, long time ago, in I think the first or in the first few lectures. But we have seen the discrete version of the Cauchy-Schwarz inequality. Now we'd like to see the continuous version of the Cauchy-Schwarz inequality, and it says the following. So basically, the Cauchy-Schwarz inequality has the following statement. It says that if f and g, let's say, are two functions, real valued functions, let's say, are integrable, then the following inequality holds true. And I'm going to write it in the following way. And in fact, you know what? Let me just write it with a color, and let me just, oops, sorry about that. And then we have here that the integral from a to b of f squared of x dx times the integral from a to b of g squared of x dx is greater or equal than the integral from a to b of f of x times g of x dx and everything squared. Right? We have dealt with this inequality, like I said some time ago, but with the discrete version. And with equality, right? So with equality, if and only if f of x is lambda times g of x, right? For lambda real scalar. All right. So that's the Cauchy-Schwarz inequality. The continuous version. Of course, this can be rewritten in a certain way, but anyway, once we see the more general version of this inequality, which we will call Holder's inequality, you will see that we can rewrite in a nicer way, let's say, or the Cauchy-Schwarz inequality. Okay, so that's the first inequality. The second one, which is a generalization of Cauchy-Schwarz inequality, it's Holder's or Holder-Rogers inequality. But usually this is known as Holder's inequality. Again, the same thing. So if f and g are defined on AB and real valued or integrable, right? Then we have the following inequality, and I'm going to write it in the following way. So we have that the absolute value of the integral of the product f times g, well, this is well known that it's less or equal than the integral of the absolute value of f times the absolute value of g. And this will be less or equal than the integral of the absolute value of f to the power p, everything to the power 1 over p times the integral from a to b of the absolute value of g to the power q. And this integral will be everything to the, oh, sorry about that, everything to the power 1 over q. All right, great. Where these p and q are greater than 1, such that 1 over p plus 1 over q is 1. So these two exponents satisfy this relation here, 1 over p plus 1 over q equals 1. And of course, you can rewrite this, you can express q as in terms of p, and you can call this the critical Holder exponent, if you want to call it. You can also state it in this way as well. So this is a generalization of the Cauchy-Schwarz inequality, because let me point out the remark. If p equals q equals 2, right? Obviously 1/2 plus 1/2 is 1. Holder's inequality implies Cauchy-Schwarz inequality. And let's rewrite it. So we're going to write it in the following way. So let's see here. The integral, the absolute value of the integral of f times g is less than and now we're just going to replace p by 2, so that would be here it's f squared dx, and I could just drop the absolute value, or maybe I should put it just for the sake of make it look 1/2, and here is just the absolute value of g squared, and again 1/2. So in other words, if we define, well, you can write this in terms of the norm. So in other words, if we define, let's just say the scalar product, let's say the inner product between f and g as, let's just say, I'm going to put it this way, as the integral from a to b of f of x times g of x dx, then Holder's inequality says pretty simple, or Cauchy-Schwarz if you want, that the absolute value of f of g is less or equal than the 2 norm, or L2 norm if you want, of f times the 2 norm of g, or the p norm and the q norm, whatever you want to call it, right? So this is the Cauchy-Schwarz inequality. Where the p norm, let's say, is given by this integral. Right, everything to the power 1 over p. All right, so that's the Cauchy-Schwarz, and of course you can interpret the Holder's inequality as well. You can say that then you can actually write that the 1 norm of f and g, or the absolute value, the 1 norm, let's say, of f and g is less or equal than the p norm of f times the q norm of g. So that's Holder. All right, so these are the two inequalities that we're gonna play around a lot with. And as a consequence of Holder's inequalities, what we call Minkowski's inequality. Like I said, I don't want to dwell too much on the proofs of these inequalities because it will take a long time. And I think this course is much more important for applications. We would like to see how we apply these. So the first, so number 3, I would like to talk about Minkowski's inequality or triangles inequality. Usually, this is it can be proved easily. Well, easily. It's a consequence, I would say, of Holder's inequality. And the Minkowski inequality states the following. So if f and g, I just say, are two integrable functions, and I'm going to stick to real values. So I don't want to deal with complex valued functions. I don't want to deal with the conjugate and so on. So I'm just going to stick to real valued functions. So if these two are integrable, right, then the following inequality holds true. And I'm going to write it in this way. So the integral of the absolute value of f plus g to the power p dx and everything to the power 1 over p is less or equal than the integral from a to b of f of x in absolute value to the power p, and the p norm is this, plus the same thing for the function g. Again, the p norm of the function g. So that's the Minkowski's inequality. And if you see here, this could be translated. This can be rewritten as, and using the notation for the norm that we have seen above, then this can be written as the norm, the p norm of f plus g is less or equal than the p norm of f plus the p norm of g. So that's Minkowski. Or the triangle inequality if you want. And of course you can replace p by 2, and of course the case p equals 2 can be proved using Cauchy-Schwarz inequality. So these are the inequalities 1, 2, and 3 can be put in the same category. So they don't require too much rather than just the integrability of the function, the functions. But now I would like to veer a little bit towards something else. We would like to see what happens when we deal with monotone functions. And there is this very famous inequality due to Chebyshev. Chebyshev's inequality. And of course, I will deal, I think I talked about the discrete version. Again, I'm gonna talk about the integral version, the continuous version. It says the following: if f and g are two functions let's say are two monotonic functions, then the following is true. And now we like to see exactly. So the following, the first thing is that if okay, let me write it in this way. So we'll have 1 over b minus a times the integral from a to b of f of x times g of x dx. This will be greater or equal, let me write in this way, then 1 over b minus a, so the average mean of f times the average mean of g. Oh, sorry about right. So that's what this is the difference between these two. Or in other words, if you would like, we can write this m fg is greater or equal than m of f times m of g, right? Where m of f is 1 over b minus a times the integral of f of x dx. And this is what we call the average mean of f. So usually you learn this in calculus 1, so, and we deal with this average mean. All right, but pay attention, we, let me point out this is a, so this inequality holds true, provided that, and this is important, provided that f and g are both increasing or decreasing. So they have the same monotonicity. Or if you want, non-increasing, non-decreasing, whatever, right? So pay attention. So this is what happens when they're both increasing. All right, and the second case, so the average mean of the product is greater or equal than the average mean is greater or equal than the product of the average mean for f and g respectively. All right, so and the second one, we can, well, as you can might guess, the inequality sign will be reversed, so we will have that 1 over b minus a times the integral from a to b of f of x times g of x dx is less or equal than the average mean of f, which is the integral 1 over b minus a times the integral of f and times the average mean of g, which is here. All right. Or you can say that if you want, we can rewrite this as mfg is less or equal than mf times mg, right? All right. And now this is important, provided that provided that f and g are let me say it like this, do not have the same monotonicity. In other words, they cannot be both increasing or both decreasing. So one of them will be increasing, the other one will be decreasing, or the other way around. All right, so this is Chebyshev's inequality. It's a very well-known inequality, very useful. And now, this, you see, so far we have done inequalities, the first three, right, which involve integrability. Now the fourth one, Chebyshev, will involve monotonicity, right? We have monotonic functions here. And now the fifth one and the sixth one will involve convexity. In any case, let me point out that any monotonic function is integrable, so you don't need to to deal with the integrability of a function. And now with the convexity, it's almost like implies continuity, except the endpoints. So in this case, we'll talk about Jensen's inequality. But this time, I'd like to talk about its integral version. So it says the following. It says a pretty nice statement. If f, let's say it's a function defined on AB, and it's a real value, is integrable, and we define this another function, let's say g, and we'll define this function on another closed interval, let's say m, capital M, and again, this will be real valued, is a continuous and convex. Like I said, this is important. And let's say M is the infimum. So we've considered the infimum of F, and capital M is the supremum of F. Right? So if we have this function g, which is defined on the interval m, with infimum and supremum of F, then we have the following inequality. This is a very nice inequality, which basically says the following. It says that g of the average mean of F, so g of 1 over b minus a times the integral from a to b of f of x dx is less or equal than the average mean of g composed with f. So it's 1 over b minus a times the integral from a to b of g of f of x dx. So that's the Jensen's inequality. Or if you want, we can write this as g of m of f if you want. All right. Can write in this way is less than m, the average mean of g of f. Right. So that's the inequality. It's a pretty nice inequality if you put it this way. So that's the integral version of Jensen's inequality. And we will see a bunch of applications of this inequality. We'll see plenty of Putnam problems solved. Well, plenty, a couple of them, I would say. And now the last inequality that I would like to discuss is what we call, it's also involving convexity. It's what we call Hermit Hadamard inequality. Okay, before that, I want to point out a remark. So if this is convex, right? So convex, when I say convex, this is what you learn in calculus 1 being concave up, right? Well, let me point out a remark. So for concave function, right? A function is concave is if negative f is convex. So for concave functions, the inequality sign is reversed. All right, great. So that's Jensen's inequality. And now let me veer towards the last inequality that I would like to discuss for this lecture is what we call Hermit-Hadamard inequality. So as you can see, these are two French mathematicians, Charles Hermit and Jacques Hadamard. both with enormous contributions in mathematics. In fact, I'd like to mention Hadamard. He was actually the one of the first one, him and de la Vallée-Pouzin, who gave like the first proof, the first actual proof using complex analysis for the prime number theorem, which was something huge at the time in number theory. It still is. It's like a very strong theorem. And I think I've discussed this theorem, and I showed you a bunch of applications when we had our number theory, analytic methods in number theory special lecture, I think. I don't know, that was lecture number 5 or something. Anyway, you can check the videos. So one of these two guys, so Jacques Hadamard, is responsible for one of the first proofs for the prime number theorem, among many other things. But he, together with Hermit, they proved the following very interesting inequality, which has the following statement. If I have a function, let's say, and this is a convex function, right, defined on an interval a, b, real value is convex, then the following inequality holds true. And I want you to look at this carefully. So if I put here the average mean of f, well, you know from the discrete, this will be between f of a plus the arithmetic mean of f of a and f of b, and f of the arithmetic mean of f of a plus b. And of course, for concave functions, let me say this, for concave functions, the inequality sign is reversed. Right? So these are the inequalities that I wanted to show you, just to. And now I would like to see applications. In fact, I'll show you a bunch of problems today. Right. So let's see applications. All right, great. And let's start with problem 1. And this problem 1, I think this was an old Putnam problem, but I also saw this in the Berkeley book for preliminary examination. So it's a Putnam A2 1964. But like I said, this also appears in the Berkeley book for preliminary exams. Let me remind you, those preliminary exams are those kind of they're like qualifying exams for incoming PhD students at the universities in North America. And this whole problem also appeared at the Berkeley preliminary exam and has the following statement. So let's consider alpha a real number, right? So I would like to show that there is no continuous function and let's say f defined on 0, 1 and positive, and with values in positive reals, such that we have the following, such that the integral from 0 to 1 of f of x dx is 1. The integral from 0 to 1 of x times f of x dx is alpha, and the integral from 0 to 1 of x squared times f of x dx is alpha squared. All right, so that's the statement of the problem. Like I said, it was a Putnam problem first before it was given in any preliminary exam. Well, usually the official trick for this problem, so let's just say the official solution is like this. So the trick is to look at the following. So we look at the integral. So let me, the following, the integral from 0 to 1 of x minus alpha squared times f of x dx. And now we will try to expand this, and we can do that easily. So this would be the integral from 0 to 1 of x squared minus 2 alpha x plus alpha squared times f of x dx. And once we do the computations here using the linearity of the integral, we have no problem. So this would be, if you want, in fact, let's do the computation. So this will be x squared times f dx minus 2 alpha times the integral of x f of x dx plus alpha squared times the integral of f. Great. And we know who these are. So the first one is alpha squared minus 2 alpha times the second one is alpha plus alpha squared times the last one is 1. And guess what? This will give us 0. Wow, that is beautiful. So we have obtained that this integral here is equal to 0. Is this guy here? Well, clearly this function inside here is already non-negative. So this will force for the function to be 0. So this forces f of x to be 0 for x, which is a contradiction because we know that f is strictly positive. So that's a contradiction. Well, so where did the contradiction comes from? Well, we assume that there exists such a function f which satisfies those three conditions given in the hypothesis. But now we reached a contradiction, and now let's see the second solution, which is faster, and I don't need to come up with this trick, but anyway, in some sense is the same. Well, maybe I could express some relationship between these three integrals here, between this one, and this one. Or maybe this will be some kind of, maybe I could express some kind of inequality between them, and that will force me an equality case, something like this. So if I have this idea in mind, maybe I could just think of a Cauchy-Schwarz inequality. But as you can see here, I have the integral of f. But since the combinations of x and f, or x squared times f. So if I would like to apply the Cauchy-Schwarz inequality, then I will have to take into account that maybe I should consider, if I want to write the function f as a square of another function, maybe I should consider the square root of f. Well, I can do that because the function is positive, so I don't have any problems with that. So let's think of this. So if you look at, you see, if we look at the last integral, so let's write it here. So I'm going to write it in this way. The integral from 0 to 1 of x squared times f of x dx. Great. And if I look at this integral of f, well, guess what? If I apply Cauchy-Schwarz inequality, and maybe this will give me something. So this will give me what? The integral from 0 to 1 of x f of x dx, everything squared. All right, let me rewrite it so that things are even clearer. So by the Cauchy-Schwarz inequality, we have. And let's see what do we have. So I'm going to write it in this way. The integral from 0 to 1 of x times the square root of x, of f, sorry, squared, everything squared, dx, times the integral from 0 to 1 of the square root of f squared, dx. And this will be greater or equal than the integral from 0 to 1 of, and let's multiply these two. So this would give me x, the square root times the square root will be x f of x dx, everything squared. So that's the Cauchy-Schwarz. But now let's identify, which can be rewritten as the integral from 0 to 1 of x squared f of x dx times the integral from 0 to 1 of f of x dx, right? Greater or equal than the integral from 0 to 1 of x f of x dx, everything squared. All right, beautiful. And now at this point, we can identify this guy here is alpha squared. This guy here is 1. Greater or equal than this guy here is alpha squared. Wow, so we have actual equality. So the equality case is attained. And let's see, when did this happen? In Cauchy-Schwarz inequality. And this happens when guess what? When those are proportional. In other words, when x square root of f is some kind of a lambda times square root of f. Well, of course, this cannot happen unless f is 0. So f of x is 0 for all x in AB, and this is a contradiction. And again, there is no such function. And we're done. So let me write it here. Therefore, there is no such function. F. And we're done. See, that was the idea. Of course, both solutions are equivalent in some sense. All right, so that was an old Putnam problem in '64. And now in a similar fashion, let me talk about so problem 2. Of a more recent Putnam problem. I think this was Putnam B5 in 2006. And the problem says the following. So for each continuous function, f defined on a 0, 1 and real valued, we'll consider these two integrals, I of f as the integral from 0 to 1 of x squared times f of x dx, and j of f as the integral of x times f squared of x dx. And now what we would like to find is we want to find the maximum value of their difference, I of f minus j of f, over all such functions f. All right. Actually, although it was a Putnam B5, which is considered to be like a hard problem, but this is actually easier than you think. In fact, we'll give two solutions. I'll show you the direct solution to this one, which is pretty straightforward, like 3 two lines, 3 lines, whatever. But I would also like to show you the official solution, which is a bit trickier. So solution 1, let's say the direct solution. Direct solution, direct proof if you want. So what we're going to do is just we compute the difference. So we have that I of f minus j of f is nothing else than just, so let's write these E2 integrals. Let's write their difference. But now if you just factor using the linearity of the integral, this is nothing else than just the integral from 0 to 1 of x f of x times x minus f of x dx. All right, great. So now we would like to do a little bit of a trick. And I would like to look at inside this integral, I would like to look at this product here, f and x minus f. And as you can see, if this product, if we add up these two, f and x minus f, f will just go away, it will just vanish. Wow, that is great. So maybe I should apply some kind of a arithmetic geometric mean inequality. So let me point, so by the elementary inequality, let's say alpha beta is less or equal than 1/4 times alpha plus beta, everything squared. We have, let's see, so we have that, so in the case of alpha is f, in the case of beta is x minus f, so we will have that the integral from 0 to 1. So we're going to use this inequality, this elementary inequality for f and x minus f inside our integral. So this would be x times, let's write it like this, times f of x times f x minus f of x dx. This will be less or equal than the integral from 0 to 1 of x times, and now I'm going to use this inequality. So this will be 1/4 times f of x plus x minus f of x. Great. All right, great. So this will be equal to, if you look here, this is the integral from 0 to 1 of x times 1/4 times x dx, which is 1/4 times, and here we will have what? We'll have the integral from 0 to 1 of x squared dx. And if you would like to, so this is b, this is 1/3, 1/12. Right? So that's the, wait, I'm sorry, I forgot. Oh, geez. This is x. I forgot, it's x cubed here. I forgot an x. Sorry about that. So this is, so here it's x squared, and it's x cubed dx. So this would be 1/16. All right, and that's the maximum. Well, the question is, when is we would like to see for which functions or is this maximum attained? So the equality case holds true if and only if, let's see, when we have equality when f of x is the same as x minus f of x, or f of x is what? Is x/2. Great. So for these functions, we actually have equality. So I of f minus j of f will be, the difference is 1/16. Great. So that was the direct solution. As you can see, just a couple of lines, well, with all explanations and everything. But also, let me show you the official solution, which is a little bit trickier. So the official solution says the following, and I want, so again, we will use Cauchy-Schwarz inequality in this case. So by the Cauchy-Schwarz inequality, we have, and let's see here, let's be careful here when we apply. So the integral from 0 to 1 of x f squared of x dx. So this is the square root of x times, and I'm going to do it in the following way. So this guy here, in fact, let me write it so it's clear, and then we'll, so it's the square root of x times f squared times the integral from 0 to 1 x times x squared of x squared. So by applying Cauchy-Schwarz, this will be, this product will be greater or equal than the integral from 0 to 1 of x squared f of x dx squared. All right, great. Or equivalently, this is the integral from 0 to 1 of x f squared of x dx times the integral from 0 to 1 of x cubed dx greater or equal than the integral from 0 to 1 of f x squared times f of x dx squared. All right, great. Or this can be translated into, let's using our notation. So this is j of f, this guy here, as you can see, this is j of f times this guy here is nothing other than just 1/4 greater or equal than this guy here, which is I of f squared. Wow, that's great. So we got this inequality, this one here. Great. So now let's evaluate the difference and let's use this inequality. So now we have that I of f minus j of f is equal to, or if you want is less or equal to, and we'd like to use this inequality, and we should be careful here, then I of f minus, so I know that I of j of f is greater or equal than 4if squared, so this will be less or equal than negative 4I of f squared. And now this guy here is just completing the squares, or AMG, whatever you want. This is clearly less than 1/16 because the last inequality was obtained by expanding. And let me put it this way. So how should I say it? So 0 is greater or equal than, let's say, negative 2I of f minus 1/4 squared. And this guy here, if you look, this is nothing other than just 4I of f squared, right? Plus 4I of f, well, times 1/4 minus 1/16. So, and that's it, and we're done. All right, so the equality case, I will leave it to you to check it out. So the equality case is holds if and only if we're going to have something like this: the integral from 0 to 1 of f of x minus x over 2 squared is 0, something like this. But this, which implies that f of x is x over 2. Because remember, we said that, well, this function, you can consider the function g is f of x minus x over 2. G is continuous. The integral of g squared is 0. Then by the first inequality that we mentioned at the beginning of this lecture, it follows that, well, the equality case, in fact, it follows that g is actually 0. In our case, in this case, it will imply that f of x is x over 2. All right, great. So that's when the maximum is attained. So again, it's less than 1 over 16. So this is the solution using Cauchy-Schwarz inequality. Anyway, both of them are pretty instructive solutions. This one is a bit trickier, I would say. But nevertheless, both of them have something really subtle either by using elementary AMGM inside the integral of using the integral version of the Cauchy-Schwarz. So both of them seem to work for this problem. All right. Now, let me do another problem. So problem 3, again, it won't be a hard problem, so it will be a similar problem to this one. So this would be, this is Putnam B3, I think, 1957. Wow, long time ago. And the problem says the following: let f defined on a 0, 1, and with values on non-negative reals be a monotone decreasing function. Show that the integral from 0 to 1 of f times the integral from 0 to 1 of x f squared of x is less than the integral from 0 to 1 of x f times the integral from 0 to 1 of f squared of x dx. See, it's kind of seems similar to this one, right? But it's not. So in this case, we would like to explore the condition that f is monotone. Well, there are two solutions for this one. The one will involve the, let's say, the double integral, like the iterated integral. Well, we can integrate with respect to one variable and keep the other variable constant, but maybe I should do that when we do when we talk about multivariable calculus, when I show some elementary multivariable calculus. And now let me show you another technique. So what we're going to do is the following. So instead of, so as you can see, we have fixed bounds there for 0 and 1. So maybe we should keep one of them to be variable. So instead of 1 there, maybe we should consider some kind of a variable t. So now we're going to consider the following function. Let's say phi. We'll define this on 0, 1. Right? And this will be a real valued function. And we'll define this in the following. Phi of t will be the integral from 0 to t of f squared of x dx times the integral from 0 to t of x f of x dx minus the integral from 0 to t of f of x dx minus the integral from 0 to t of x f squared of x dx. All right, great. So this is my function. And now what we're going to do, so clearly phi of 0 is 0, so there's no question about that. And we would like to, well, if we show that we would like to get some information about phi of 1. So in other words, if we show that phi of 1 is greater than phi of 0, which is 0, then maybe well, not maybe, the conclusion of our problem follows immediately. In other words, if we prove that, so we want to show that phi of t is greater or equal than 0, is not negative for all t is 0, 1. So if we show that phi is non-decreasing, then we're done. In other words, let's compute the derivative. I have no problem with this function with phi, because clearly I can differentiate the integral. I have no problems with it. All right, great. So now, so we compute the derivative. So we would like to show that the derivative is greater than 0. So let's do that. So we have that phi prime of t, this guy is, so in the end, when you apply the product rule to each one of them, so this will give us, okay, so it will be something like f of t times the integral from 0 to t of x minus t, when you factor here, times f of t minus f of x, right, f of x dx. And clearly, this is non-negative, right? Because the function, let's keep in mind, here we use the fact that the function f is, let's not forget that the function f is decreasing. We use this fact. All right, great. So this means that phi is non-decreasing, and so phi of 1 is greater or equal than phi of 0. But phi of 0, like we have seen, is 0, and the conclusion follows. And that's it. That's the proof of this. So you see a couple of lines. This was a very nice problem as well. We will see, like I said, another proof for this one. All right. Now, let me play around with some other type of inequalities, which are a little bit more complicated than what we have seen up to this point. And so problem 4 was a very nice problem from the Romanian National Math Olympiad. I think that was back in 2004. And it says the following. So let f, it's a function defined on 0, 1, real valued, be an integrable function. Right, such that this condition holds true. So the integral of f is the integral of x times f, and both of them are equal to 1. So we would like to show that the integral of the square of f is greater or equal than 4. So that's what we would like to show. And of course, if you look at this, and well, you'll be tempted, well, since we don't have too much information, maybe you will be tempted to just use the Cauchy-Schwarz inequality, right? So if you, for example, we can apply the Cauchy-Schwarz inequality. If you look, let me just play around with this. That so, for example, you see, I can play around with Cauchy-Schwarz in this way. Right. I can apply the Cauchy-Schwarz inequality to f and 1. No problem. This is 1, and this is 1. So I'll get that the integral of f squared is greater or equal to 1. Well, not good enough. Right? Well, maybe, so I use this condition of the that the integral of f is 1. But what if we use something like this, such as the integral of f squared of x times, this time, let's say, maybe the integral of x squared dx is greater or equal than the integral from 0 to 1 of x f of x dx squared. Again, Cauchy-Schwarz. Let's write here by the Cauchy-Schwarz inequality. We have these. So from this second one, this guy here is 1/3. This guy is 1. It follows that the integral of f squared of x dx is greater or equal than 3. Again, not good enough. And if we add them up, you will get even worse. We'll get the integral of f squared is greater or equal than 2. So I can get 1, greater or equal than 1. I can get greater or equal than 2. I can get greater or equal than 3. But that's not good enough. I need to get greater or equal than 4. So maybe I should do something, some kind of a trick that will allow me to use both conditions. As you can see, I used separately. In fact, there are 3 conditions there if you want. Or if you look closely, you will see that I used only 2 conditions, not all 3 of them at the same time. So I used the fact that the integral of f is 1. Then I used the second inequality, I used the fact that the integral of x times f is 1. But I didn't use that both of them are equal to 1 at the same time. So maybe I should do something. So not good enough. So maybe I should do something. Well, let's play around with these. Maybe I should make use of that. I should think of some kind of a form. Maybe it can be represented by something. And let's do it in the following way. So let me show you a magic trick. So look at this guy here. 2 is the same as, 4 is the same as 2 squared. But this 2 squared can be written as 3 minus 1, everything squared. Right? So far, it's just basic algebra. But now I can do the following. I can write this 3. In fact, no, let me write it in this way. This is also 3 times 1 minus 1 times 1 squared. And now maybe I should do something here. This is 3. Maybe this one here will be given by the first or the second integral, meaning the integral of xf minus 1 times the integral of f. And this everything squared. And this will be equal to, if you do all this algebra here inside, the integral of 3x minus 1 f of x dx squared. Wow, great. And now, by the Cauchy-Schwarz inequality, we have that this integral here, the integral from 0 to 1 of 3x minus 1 times f of x dx squared is less or equal than the integral of 3x minus 1 squared times the integral from 0 to 1 of f squared of x dx. All right, great. So we know that this guy is 4, all of it together. And now we only need to compute this integral. But this guy here, if we, let's see what this is. Well, let's do the computations. In fact, let's do it separately. This guy will be something, and here this guy is just the integral from 0 to 1 of f squared of x dx. All right, great. So the only thing we need to do is just to evaluate this integral, and I'm boxing this, I'm circling this in red because this will be a special polynomial there. I'm not divulging anything yet. So now I'm just playing around with this, like Cauchy-Schwarz, some elementary tricks without saying anything, where it comes from, so nothing like that. But I will explain once I do the second solution, I will explain immediately where everything comes, where does it come from. But anyway, I'm not gonna spoil it out right now. Just be patient for a couple of minutes. So now let's just compute this integral. The integral from 0 to 1 of 3x minus 1 squared. Anyway, this is just basic algebra, but let's do it. This will be 9x squared. Anyway, so this is 9 times 1/3 plus 1. So this is 3 minus 2. Oh, wait. Oh, okay, sorry. 3 minus 3 plus 1. Okay, so this is 1. So this guy is 1 here. So of course, guess what? This implies that the integral from 0 to 1 of f squared of x dx is greater or equal than 4. Beautiful. But okay, this is a trick, a magic trick if you want to put it like this, but what does it come from? I mean, why did you pick that? Why did you do that? Maybe you can do something else. All right, and now let me explain it. So let's do the second solution. It's a more conceptual solution. All right, so if we look at the system of equations, so if we look at the system of equations, so let's say the integral from 0 to 1 of f of x dx is 1. And let me put it this way, and the integral from 0 to 1 of x times f of x dx is 1. Right? Maybe the best way to look at this, to approach this, maybe if it's, if we would like to see this as you can see, I have a combination of polynomials there, right? Here is the 1, and here is x. So maybe I should see what kind of polynomial does this system of equations satisfy. In other words, we are looking for a linear polynomial, let's say f, or a linear function that satisfies S. All right, let's do it. So, in other words, so we look for functions like this, f of x equals x plus b, such that f verifies S. And now, by replacing this, we will have that the integral from 0 to 1 of ax plus b dx is 1, and the integral from 0 to 1 of x times ax plus b dx equals 1. All right, great. And now I'm going to leave this to you as an exercise to solve this. It's just a simple system of two equations, two variables. So I'm pretty sure you can do this. So we'll determine that a is 6 and b is -2. So the polynomial that we're looking for is f of x is 6x minus 2, or if you want, we can factor here is 2 times 3x minus 1. Wow. So that's the best polynomial that will satisfy those two integrals at the same time. So this is the right polynomial of the right linear function that will satisfy these two conditions here. Great. So now in this way, well, you can do it like this. You can apply Cauchy-Schwarz to this. It doesn't really matter. Or you can just look at this integral. So we look at this integral. So we're going to take the square of this. Actually, this is a pretty standard minimizing integrals technique. So basically, we'll look at this integral, so which is non-negative, of f of x minus 6x minus 2 squared dx. And here, but I'm just going to leave this to you as computations. So details, I'll leave it to you as an exercise. This will be nothing else than just the integral of f squared of x dx minus 4. And the conclusion follows. And that's it. Of course, so that's the technique here. Or like I said, you could have, once you put your hands on this polynomial, you can apply Cauchy-Schwarz to f and 6x minus 2. So, but basically it's just pretty much the same thing as we have seen in the first solution. All right, so this is a very nice problem. And in fact, in the recitation, when we'll talk about, we'll do a similar problem to this one. When in fact, we would like to see what happens if we add one more condition, such as the integral from 0 to 1 of x squared f equals 1. So maybe we can get, instead of 4, maybe we can get another number. And that number, it will turn out to be equal to 9. But anyway, we'll get there. Now, let me do another problem, a similar one, but now involving, so this was problem number 4, now problem 5. So now problem 5 says the following. Suppose that f is a C2 function, 0, 1 real value, such that we have the following conditions, such that f of 0 is the same as f of 1, is the same as f prime of 0, and all three of them are equal to 0, and f prime of 1 is 1. So show that the integral from 0 to 1 of f second prime of x squared is greater or equal than 4. So in this problem, as you can see, we are dealing with a C2 function. So let me remind you that the class of C2 functions is the class of functions which are twice differentiable and the second derivative is continuous. In other words, it's good for us to deal with this because we can integrate by parts, so we don't have any problems. And as you can see, I'm estimating there the 2 norm of the second derivative. So the ingredients seem to be pretty much clear. So probably we'll have some kind of a Cauchy-Schwarz inequality combined with some integration by parts. Definitely integration by parts should be a good tool to use in this case, since we have some information about the function f at the endpoints, and also we have information about the first derivative at the endpoints. So definitely that this could be very useful. So let's see. So the thing is that we would like to consider a function in the following way. So consider the function, and let's define a function, let's say h of 0, 1 real valued, and we'll define it in the following way. H of x will be f, and we'll subtract some polynomial, maybe a cubic, so minus x cubed minus x squared. Something like this. And now we'll see why. So clearly, we like to see what happens to the function h at the endpoint. So clearly, h of 0, if we plug in, is 0. H of 1 is 0. So both of them at the endpoints are equal to 0. And if we compute the derivative at h prime of x, well, this will give us f prime of x minus 3x squared minus 2x. Now clearly, and this will give us, if we evaluate the derivative of h at the endpoints, so clearly we'll have that h prime of 0 is 0. And let's see, h prime of 1 is again 0. Wow. Great, beautiful. Absolutely beautiful. So now what I would like to do is the following. So now we evaluate the following integral. And let's call this integral I. So this will be the following. So there is the integral from 0 to 1 of, and now let's be careful here. So this would be, again, I'm just gonna, you look at this guy. So it's say 4 times 3x minus 1. So I'm going to take a multiple of the function 3x minus 1 times h second prime of x dx. And this guy here, if we do integration by parts, and I'm going to leave this to you as an exercise, so details, I'm going to leave them to you as an exercise, but I would like you to do to take care of these details, to carry on these details. You know how they say, the devil is in the details, so make sure you check them out. And this will be equal to 0. Great. And now pretty much I can the second derivative, you know, so now if I would like to look at the integral from 0 to 1 of the second derivative of f, square of that, right? I can compute it here, right? Keep in mind that from here it follows that the second derivative of h is f second prime minus 6x minus 2. Wow. Again, the same polynomial. See? The same polynomial. Great. So now this guy here, it will give you by some computations, the 4 plus the integral from 0 to 1 of h second prime of x squared dx. And of course, this integral is non-negative here. You can neglect this if you want. But this will be greater or equal than 4. And that's it. So that's the solution of this problem. So basically, the ideas are hidden in the previous problem. So all right. And of course, you can play around. You can tweak functions like this. You can consider plenty of functions, and you can play around with derivatives. Anyway, I'm not going into detail. So I just wanted to show you a problem that could be using ideas from the previous problem. You can derive something like this using also combining with some integration by parts. Now, let me do another problem, which so problem number 6, which is a kind of a Poincare type inequality. This is a very old problem, published in Elemente del Matematique, I think in 1983. I always do this problem. I think it's one of my favorites. But anyway, the problem says the following. So let f be a function from real value defined on 0, 1. So be a C1 function such that f of 0 is f of 1, and both of them are equal to 0. Show that the integral from 0 to 1 of f prime of x squared dx is greater or equal than 12 times the integral from 0 to 1 of f of x dx squared. So again, as you can see here, we deal with the C1 function, and we deal with the first derivative again, and we would like to minimize in some way the integral of the derivative square. So maybe we can have in mind some kind of a combination between Cauchy-Schwarz inequality or and integration by parts. But as you will see, we have to do this in a smart way. So that's the thing. We have to do it in a smart way. So let's see. So first, let's check this integral out. Let's look at this guy here. Just let's look at this innocent integral here. Maybe we can do something. Maybe we can integrate by parts. Maybe you can put here an x prime. So we have, let's see, maybe you can do some integration by parts. So this would be xf from 0 to 1 minus the integral of xf prime of x dx. So this would be 1 f of 1, which is 0. So great. So this is nothing else. So this guy is 0. Negative the integral from 0 to 1 of xf prime of x dx. All right, great. So let's apply Cauchy-Schwarz now. Let's see what's going on, because we just used the first one. So by the Cauchy-Schwarz inequality, let's see, what do we have? So we have that the integral from 0 to 1 of f of x dx squared, which is the integral from 0 to 1 of, okay, negative, it doesn't matter, x f prime of x dx squared. This guy is less or equal than the integral from 0 to 1 of x squared dx minus the integral from 0 to 1 of f prime of x squared. Wow, looks like we're getting something. But guess what? This guy is here, it's only 1/3. I need 12, not just 3. So not good enough again. Not good enough. All right, let's see, maybe this trick didn't work. So let's call this 1 here. Let's try something else. Let's try something like this. So instead of x prime, maybe I should put x minus 1 so that I can use the other one as well. So x minus 1 prime times f. So this would be, let's say, x minus 1 times f of x from 0 to 1 minus the integral from 0 to 1 of x minus 1 f prime of x dx. So this guy here, it will be equal, so 1 will be gone, so it will be negative f of 0 minus the integral from 0 to 1 of x minus 1 times f prime of x dx, which is f of 0 is 0. So this guy, let's keep in mind that this guy is 0. So this is negative the integral from 0 to 1 of x minus 1 times f prime of x dx. Great. Let's do again Cauchy-Schwarz. I want to see what this will give us. So by the Cauchy-Schwarz, again, we have, let's see. So the integral from 0 to 1 of f, everything squared, which is, first instance, is this guy here, right? Squared. Or if you want, this is nothing else than just x minus 1 f prime of x. This guy here is less or equal than, let's write it here, then the integral from 0 to 1 of x minus 1 squared dx times the integral from 0 to 1 of f prime of x squared dx. And now the only thing we need to do is just to compute this guy here. And let's see what this will give us. So this is nothing else than just the integral from 0 to 1 of x squared minus 2x plus 1 dx, which is what? So it's 1/3 minus 2 1/2 plus 1. So this is 1/3 again. So this implies that the integral from 0 to 1 of f prime of x squared dx is greater or equal than 3 times this. So basically the same thing. Not good enough again. Oh my, this is it's a pain right now. All right, so maybe we shouldn't do this. Maybe we should look at this. Let's call this 2 here. So in other words, we have the following. So let's restate. So far we have the following. So let's restate the relations 1 and 2. So 1 is, let's say, the integral of f is negative. So the integral of f is negative x times f prime of x dx. So that's 1, which I already wrote that. And the second one is that the integral of f is nothing else than just, what is it? So the second one is negative x, the integral of x minus 1 times f prime of x dx. So maybe we could use these two relations at the same time. So maybe we should. And what I was thinking is maybe so this guy can also be written as the integral of 1 minus x times f prime of x dx. Great, let's add these two. So add 1 and 2, and we get that, we obtain that 2 times the integral from 0 to 1 of f of x dx is the same as the integral from 0 to 1 of, this will give us 1 minus 2x f prime of x dx. All right, great. So let's square this. So finally, we will get the following. And now we can apply one more time the Cauchy-Schwarz inequality we have. So let's square this. So we'll have 4 times the integral from 0 to 1 of f. Everything squared is the same as the integral from 0 to 1 of 1 minus 2x f prime of x dx squared. And now, by applying the Cauchy-Schwarz inequality, we have the following. We have that this is less or equal than the integral from 0 to 1 of 1 minus 2x squared dx times the integral from 0 to 1 of f prime of x squared dx. Great. And now the only thing we need to do at this point is just to compute this guy here. So maybe that will give us something. So let's do that. If this, maybe we can be lucky here. So let's compute this integral. So the integral from 0 to 1 of 1 minus 2x squared is nothing else than just this guy is 1 minus third. So this will be, which will give us And this is 1/3, exactly what we needed. So this guy is 1/3. And now finally, so this implies that, so this gives us finally that the integral from 0 to 1 of f prime of x squared dx is greater or equal than 12 times the integral of f of x dx everything squared, which is exactly what we wanted to prove. And that's this problem here, right? Well, as you can see, again, it was a little bit tricky. You cannot apply just directly the Cauchy-Schwarz inequality. You have to use both conditions on the boundary, right? You have to use that the fact that the function f is 0 on the boundary. All right, so now we have one more problem to do. And after this, I think I'm going to stop. So this would be problem number 7, which was given at the recent Putnam exam. And the problem says the following. So it was a Putnam A3 in 2017. The problem says the following. So the following statement, let A and B be real numbers with A less than B, and let f and g be continuous functions from the interval, closed interval AB, right, to the positive reals, 0 infinity, right, such that the integral of f is the same as the integral of g. But the two functions are not the same, so their f is different than g. And now for every positive integer n, right, we define the following sequence. So we define the sequence, let's call this I sub n, which is the integral from a to b of f of x to the power n plus 1 over g of x to the power n dx. Now we're asked to show that the sequence is increasing, so I1, I2, I3, and so on is an increasing sequence. With the limit as x approaches infinity of I(n) is infinity. So that's what we're, this is the statement of the problem. So this was a Putnam A3 in 2017. You can see. All right, so, well, since I don't want to deal with too many A's and B's, so without loss of generality, let me show you the solutions here. So without loss of generality, assume that A is 0 and B is 1. So I'm going to just work with the interval 0, 1, so everything in. So first I'm going to show that the sequence IN is increasing. So now, so we show that the sequence IN is increasing. Great. And first, we would like to fix I sub 0 because the sequence starts from n equals 1, but I would like to fix I 0 as the integral from 0 to 1 of f of x dx. All right, beautiful. And now what we're going to do, I'm going to do the following. So by the Cauchy-Schwarz inequality, we will have that I1, which is equal to the integral from 0 to 1 of f squared of x over g of x dx times the integral from 0 to 1 of g of x dx is greater or equal than the integral from 0 to 1 of f of x dx squared, right? So this is by just Cauchy-Schwarz. Or since we know that the integral of f is equal to the integral of g, so, or equivalently, you can infer that I1 is greater or equal than I0. Great. So we have this. And now, so next, we show that we have the following inequality. We show the following inequality. And you'll see why I use this trick. So I'm going to show that I(n) squared is less or equal than I sub n minus 1 times I sub n plus 1 for all n. Great. And let's see, you will see immediately why this is important. Let me denote this by star. So first, let's show this inequality. So this is equivalent with, so we have that, let's write this, that I(n) star. So this integral, this will be the integral from 0 to 1 of f to the power n plus 1 of x over g to the power n of x dx squared, right? So that's our integral. And we're going to write it in the following way. So this would be, let me write it in this way. So I'll write it in this way so I can, okay, great. So I'll write this as the square root of f to the power n plus 2 of x over g to the power n plus 1 of x times the square root of f to the power n of x over g to the power n minus 1 of x. It's exactly what I'm writing in this way because this is what I would like to obtain. And so this can be easily can be written in this way. And now by applying the Cauchy-Schwarz inequality, so again here I'm applying Cauchy-Schwarz inequality. Guess what? This will be less or equal than the integral from 0 to 1 of f to the power n plus 2 of x over g to the power n plus 1 of x dx times the integral from 0 to 1 of f to the power n of x over g to the power n minus 1 of x dx, which is indeed, this is n plus 1 times I sub n minus 1. Great. So at this point, we approve this inequality. We prove star, right? So now let's see how, let's rewrite this inequality. So let's see how we can use this inequality here. Right? So we'd like to see that. So now clearly we have what do we have? So we have that, let's rewrite this. So I(n) plus 1 over I sub n is greater or equal than I(n) over I sub n minus 1. And we keep going inductively until we get to I(1) over I0. But we know that we have proven it at first by using Cauchy-Schwarz that this is greater or equal than 1. So therefore, this implies that I(n) is increasing. Great. Right, so this sequence is increasing. All right, and now let's show the fact that that the sequence actually diverges. So now we show that In diverges to positive infinity. First off, let's we show that there exists an alpha, let's say 0, 1, such that f of alpha is strictly greater than g of alpha. Anyway, I think this is quite easy to see. Maybe I'll leave it to you as an exercise. But let me just verbally tell you. So basically, you assume that for all x, f of x is less or equal than g of x. Then you take, you consider the difference, g minus f. You know that the integral of, so you denote h, g minus f. You know that the integral of h is 0, but you know that it's continuous, it's non-negative. So therefore, this will enforce that the function h is 0. In other words, f equals g, but that's not the case because we assume that f is different than g, so that's a contradiction. So that's the first thing. All right, great. And now, since we have this information, now it's now we can define. So we can define the function, and I will define phi, define on 0, 1, and this should be with values in positive reals, and phi of x will be f of x over g of x. Great. And let's say a few things about phi. Clearly, phi is continuous. Right? And since phi of alpha is greater than 1, it follows that there exists a neighborhood, let's say, of 0, 1. So it follows that there exists, let's say, an interval m in 0, 1 with phi of x strictly greater than 1. For all x in that neighborhood, let's say m, capital M. Great, since f is continuous on this closed interval m, it follows that it has, by Weierstrass theorem, it has an infimum and it has a supremum wherever these two are attained. So it follows that, so moreover, it follows that that the infimum, let me write it here, the infimum of phi of x is, let's say, some number phi of x naught, which is strictly greater than 1, and this is for all x in this interval m. Great. So therefore, thus this implies that phi of x is, let's say, strictly greater than lambda, right? So for some lambda, so there exists a lambda greater than 1 such that phi of x is greater than lambda for all x in m. Great. And now at this point, we can write our integral or sequence as in the following way. We can write it as In is the integral from 0 to, let's say, m of f of x times phi to the power n of x dx plus you can write it in this way. And this, we can neglect the first one and the last one. And this will be greater or equal than this integral from m to m of f of x times phi to the power n of x dx, which is greater or equal than lambda to the power n, because phi of x is greater than lambda, so we're going to take it out, times this integral of f of x dx from m to m. But this guy here, we can use the mean value theorem, and we can express this. So this guy here is m minus m times f of c for some c in mm. And guess what? This is quite clear that at this point, this would be equal to lambda to the power n times m minus m times f of c. Which, of course, this is positive, so I don't have any problems with that. And now, clearly, finally, this will give us that the limit as n approaches infinity of in is positive infinity. And that's the end of the problem. Anyway, it's a very nice problem. All right, I think I'm going to stop here for this lecture. I will continue with 15.3, where we'll discuss about limits of integrals, how to, and also there will be some power series involved, series of functions involved, and so on. Okay. I think it's a good place for me to stop now. Thank you.